Hello guys, welcome to Freebirds Crew. So first of all, thanks for 1000 subscribers on our YouTube channel, and thank you guys, thank you for your support. And this is our new playlist on neural networks, in which I explained detailed about neural networks and the mathematics behind it, how it works and its architecture, everything. So let's start our video. So this is how the neural network looks in its diagrammatical form. It has some input layers, hidden layers, and the output. So the data that it got from the input layer get processed in its hidden layers through the activation functions, through its methods, functions, and everything that we can add up in those hidden layers. And then it gets the output that we want to deserve. So the neural network is simply got from the brain. As we know that I made a video on the neural link of Elon Musk, as you can see on the I tab here, and in this video I'll tell you about all the brain functions, that how neuron works. So the same thing applies here. It is technically based on the neurons in our brain. So neurons is equal to the neural network in machine learning or deep learning. So similarly, the neurons have its dendrites from where it can get the data, and it can process in the nucleus, and then it can pass through the other layers, and it can get its response to the axon terminal, and it can goes to our different body parts. So same thing happens here. It can get data from input layer and then processed in hidden layers and then get the output. And in this session I will tell you about all things about neural networks, its real life application, the types of neural networks, and loss functions, activation functions. These are the key topics that we need to learn about the neural networks that will help in us building our machine learning and deep learning strong. So in a bookish way or something like that, I can tell you about the neural network is just a mathematical function that can maps each input with the desired output, by recognizing the patterns or by data pre-processing or processing. It just resembles the human brain, main thing. So these are the key components in neural network. The first is the input layer, I. Second is arbitrary amount of hidden layers that we can use to process our data, and then the output layer. And then there are some weights and biases added to each layer. As you see that it has weights. So weights are a kind of a amount of influence that it can over the other layer, that if this layer has more weight than this, so this layer has more influence on this. The weights are just to tell you that that if the program goes in this way, it can have a better output. Like if I have two roads in a way, and the road 1 has more influence than the road 2, it can go to the road 1. Similarly, there are the biases in our neural networks. The biases are just to get the data in a very fit manner, that our data we want to move into the right or move into the left, or in which direction we want to move our data or move our result that we get through the neural network. So I hope you guys understand about the neural networks. And the fifth thing is the choice of activation function in each layer. It's sometimes called sigmoid, ReLU, or tan-H. Everything you want to use, you can use it by correctly understanding your data. So in next video I will tell you about the application of artificial intelligence in neural networks, and how we can use neural networks to maintain our daily life easy by creating the fun programs or fun applications with neural networks. I hope you guys likes it. Thanks for being here. Please like, subscribe, and share our YouTube channel. So the first application is classification of data. The classification is just like a thing that we can classify data according to their categories. Like if I have an image or I have a category, Like I have a image of a cat and dogs, and I want to categorize those images. So with the help of neural network and the part of neural network that is known as convolutional neural network, I can done it very easily. As you see in the image that I input image and use a convolutional 2D neural network, and the max pool is my activation function that we can discuss in our next videos, and it can make a fully connected neural network and get output as cat. So in this way, the neural networks helps you to classify your data in certain categories. And the next part is anomaly detection. So anomaly is basic outliers in your data, the data that is not to be a part of your actual data. Those are called outliers. Like if I have a data of numbers from 1 to 100, and there is a number that is in negative or more than 100, so that numbers are not that numbers are not needed in my data, so I want to delete those numbers. So anomaly detection is used the same way. It can detect those outliers and then delete it. As you can see in the image that I have a mushroom image here. It has more contrast, more darkness, and the other effects also that are not needed for my data. I just have to run a anomaly detection algorithm on that, and just compress the data and found this image. So that image is of the lesser size with actual parameters and actual variables. So that image is the best data that I can have. So my other application is speech recognition. As we know about the Google Assistant, Siri, Alexa, they are all our work on the artificial intelligence or neural networks. So with the help of neural network, I can made a speech recognition algorithm also. It can detect my speech. It can detect my speech and recognize that what I said. As you can use one of two libraries of Google or Microsoft, that is speech recognition libraries. You can make your own speech recognition system. The next thing is audio generation. So audio generation is that thing that if you have given some input files as a input to the neural network, it can generate the music based on that genre or singer or others like thing. So you can have a full view on that link that I gave there. It has the total information about the Google voice search or your voice encoders, decoders, that how the waves work and how you can generate music. Like in this image you see that if I can give the data to the network, it can just get the output, and that output is its next input. So in this way it can generate a music in that way. So you can surely go to this link and read out the whole thing. You can basically understand about what is audio generation. So our next thing is time series analysis. So time series is a data that is generated by time to time. As I know that the stock price data is a time series data, because stock price changes about every second or every minute, so it can have data of about months. So that is called time series data, that which has time, which has data, and which has spikes. That sometimes the stock is up, sometimes the stock is down, and at the what point the stock is down, what time the stock is down and stock is up. So that is all things are accumulated in the time series data. So with the help of neural network, you can surely analyze the time series data and can also predict to a very much extent, like about 70 to 80% accuracy, that what's the next stock price is. It's not the 100%, because the stock price is not only based on or dependent on your calculations, it also depends on the weather conditions and other factors also. So our next application is spell checking. As you know from the word, that it can check your spellings of your words that you give into it. Like I gave a word of according that is wrong, and it can use the algorithms and neural network to get the correct word. So in this way you can make your own neural network program to spell checking. And our next application is character recognition. So character recognition is just like the characters that are not in a readable form, or the human written applications, or the things that are not understandable by humans. So with the help of neural network, you can detect that what is written in here. Like if this is the A that is written by a human, and it can convert into the pixels form, and then it convert to the numpy array form. In this way, you can detect the characters or handwritten characters with the help of neural networks. Other application is machine translation. So translation is just like a translation from one language to another language. Like I can give a machine a language of English, and I can tell the machine to translate it into the Japanese or Chinese. So it can also translate into the other forms. So basically, machine translation is the simple thing that can translate by phrase your data into other language. And our next thing is, and the last is, image processing. So image processing is to process the image, to get the useful information from the image, to enhance the image, or to do various calculation or functions on the image. So with the help of neural network, you can do that. Like our first application, that is classification of image processing, it is also a part of image processing. So with the help of that, you can surely do your work with the neural networks. I hope you guys like this video. If you guys like this video, please give it a like and subscribe my YouTube channel. So this is our neural network, the least easiest form that I have here. It has the input layer, it has the weights, it has the hidden layer, and it has the outputs. So you see here, our output is depend on the weights and biases that we can add to the neural network. So the more the correct weights and biases you add to your neural network, the more accurate it is. So basically, each neural network is consist of two parts. First is feed forward, second is back propagation. So feed forward means you just keep calculating your predicted output y by using those weights and biases, and that's it. And the second process is back propagation. Back propagation happens when your loss is more than your actual values. Mainly the loss is just like a thing that your actual value and your predicted value has a very large difference. Just say your actual value is 1000 and your predicted value is 500. So there is a difference of 500 that is very large. So in those phases, we need the back propagation. So back propagation is simply the things that we need to keep updating our weights and biases to make it more accurate and to make it more genuine, that it can give us the correct output. So as you see in this diagram, I can give it to the inputs, weights and biases. It can go here like the slope. As you know, the formula of a slope is mx plus c. So here you can see that works like this, and it can has its activation functions and can again go into further and again go into the result. And after it get a result, it also calculate the loss, that what is the loss between the actual and the predicted value. If it is more than the threshold, so it can back propagate. It can just update the weights and biases and then again calculate. So on the basis of those, our neural network is of two types. The first is feed forward, second is back propagation. So feed forward are the simplest neural networks, in which you have to just give it the input values, weights and biases, and it can have to work on those and can generate the output. Simple. So as you see, this is my code here. I use the sigmoid activation function that just calculate on the basis of your input and weights and can get you the result. We can discuss on the activation function in our other videos soon. So as you see that this is a simple feed forward neural network. There is no complex things here. So Our other things come here, like when the loss is more, that is back propagation. So back propagation is just worked on the thing that is called the loss. So if there is more loss, we need to back propagate and update the weights and biases. So in order to make it happen by adjust the weights in a very appropriate way, we need to know about the derivation and calculus. These are the two topics of mathematics that you need to know, because we need to know the derivatives of loss functions and with respect to their weights and biases. So you have to calculate those if you are trying to get it by its mathematical way. If you are not, then there is no need to tension. There are all mathematical functions present in the Python. So by using this graph, you can see that the gradient of the slope tells us the direction we need to move toward to reach the minima. So if our weight just move from increase to just lesser value, it can have reach the minima and can minimize the loss also. So if we have a derivative, we can simply update the weights by increasing and decreasing the weights and biases. This is known as gradient descent, the term that you can see on the internet nowadays, that gradient descent is a very big cliche term, but it is not like that. It is just simple term that you just have to know the derivatives, and by using that you can just update your weights and biases and make your neural network a good one. So as you see that the loss function does not have the weight and biases in here, so due to that we need to use the chain rule here. The chain rule is just like that. We need to make this function to its initial form, like this multiply by our this formula, and where you know that the z is equal to wx plus v, that is weights and biases. So with the help of that you can easily calculate the derivatives of the sigmoid function here, and plus you can get the input value. So this is a kind of mathematical tricks I have to use here, but this is not all you need to do, because if these things can done in a very generic way, you can get the output like this, and with the help of this output you have just implement the same output in our program. Like here the way to update by this, like it has the input layer function, and I can use it to transpose and then 2 into the actual output, what is the predicted output, and then sigmoid of the output. So at last we just need to add those updated weights in place of our actual weights. So in this way all your things can be done. So now we have the complete Python code for feed forward and back propagation. Let's apply our neural network on an example to see what it does. So guys, you can see here that all our data is here, that is x1 and x2, and this is the actual output, this is the predicted output. So the actual output and predicted output has some differences here, that its first and last value is not correct, but is the second, third is correct. So this is happen why? Because we use our iterations to only a very small value, like only to 10 to 15. So the lesser the iterations, the more the loss. So we just need to make our iterations more and keep updating our weights and biases. Like I written here that our neural network should learn ideal set of weights to represent this function. Note that it isn't exactly trivial for us to work out of weights just by instruction alone. Let's train the neural network for 1500 iterations and see what happens. Looking at the loss per iteration graph below, we can clearly see that loss monotonically decrease towards the minimum. This is consistent with the gradient descent algorithm that we have discussed earlier. Like we just have to keep updating our weights and biases and need more iterations to make our neural network looks perfect. As you see the graph here, that at only the 10 to 15 iterations the loss is very much, but as soon as the iterations become more, the loss becomes less, and at 1500 iterations the loss becomes negligible. So this is what happens when the iterations are of the 1500 iterations, like our actual value and predicted value is almost the same. So this is what happens when we do our work with the very generic way, with knowing all the formulas behind the neural network, because there is just need to learn the derivatives and calculus, that you need to follow those rules by using the gradient descent in your back propagation neural network. So that's all, guys. If you have any queries regarding this, please ping me and mention your queries in the comment section. If you guys like this video, please subscribe my channel. Welcome to Freebird's Crew. So this is our new video, the activation functions. In this video I will tell you about what are activation functions, when they are used, why they are used, and the derivatives of activation functions. All things are explained in this video. So this is the most important video in our neural network playlist. Hope you guys watch it to full, and please let us know if you have any queries, and also subscribe our YouTube channel. So let's start the video. So in neural network, as you know that the brain neurons are the replicas of the neural network. So every neuron will do two computations. The first is the linear summation of the inputs, and that you see that if you have two inputs, that x1 and x2, and with the weights w1 w2 and with the bias at b, so the summation occurs in this scenario, that w1 into x1 plus w2 into x2 plus bias. So in this way the summation of inputs can be done. So other thing is activation computation. The computation decides that whether a neuron should be activated or not by calculating the weights and then sum it and then add the bias in it. The purpose of activation function is to introduce the non-linearity into the neuron. It makes it easy to understand the data, the variety of data, to adapt and to check the pattern of the data, and to differentiate between the outputs also. So in this diagram, that it has the n inputs and n weights with those inputs. So these are all added into the summation function, where they are all added and with the bias add also, and then it again goes to the activation function, and where it calculate the loss also, and if the loss is above the threshold, it can go back with the help of a back propagation algorithm and can just update the weights also. So after updating the weights, it can again repeat the cycle. So this cycle will repeated up to your iterations that you have. Like if you have the 1500 iterations, so it can repeat cycle about 1500 times. If you have the 2 or 3 iterations, it can repeat the cycle about 2 or 3 times only, and then after the cycle completed, it can give you the output. So this is the non-linear type of data, and this is the question that is asked around there, that why derivatives and differentiation is used. That as you know that we have to keep updating our biases and weights to make our neural network more accurate and more precise. So when updating the curve or updating the weights or biases, you have to know that the direction in which you are moving is correct or not. So to know the direction, we have to just use the derivatives of the functions with respect to their weights and biases. So this derivative can helps you to check that the direction is right, and how much you change the curve or how much you change the slope is correct or not. So this is why the differentiation is the most important topic in machine learning and deep learning. So as you know, the first name is identity, that is the linear relationship thing. So as you know, as you see that its function is fx is x. So when we are using this function, that we have to how we have to know that we are moving in a correct direction with respect to this function or not. When we calculate the derivative of that function, we get the answer that it has 1. If we are moving in a linear direction, only then it can be the true thing. And similarly, the ReLU function that we have here, rectified linear unit, its output can always be 0 or 1, means true or false. So that when you are using this equation from the ReLU function that has 0 and x, then how can we know that the values are that we are getting is correct or not? So with the help of derivative of that function also, we can get the value like 0 and 1. So it's always 0 and 1. So in this way you can use the derivatives to make sure that you're moving in a right direction. So this is the graph of all the derivatives, and this is the types of vector functions. The first is sigmoid. So the sigmoid can take any range of real numbers and return the output value which falls in the range between 0 and 1. So the sigmoid and the tanh or hyperbolic tangent activation function cannot be used in network with many layers due to the vanishing gradient problem. We can discuss about this problem in our next videos also. So the sigmoid function produces the S-shaped curve. Mathematically, sigmoid can be represented by this formula, that is 1 by 1 plus exponential of minus x. So in using the Python language, we can have this function here, that sigmoid. We can just make a sigmoid this, and we can make the derivative of sigmoid also, that s and ds. So this is our data, and we can get the sigmoid of that data also, and then we can just generate the plot here. This is our plot, and the plot is look like this, that first curve is sigmoid, second is its derivative. As you see that the derivative is close to 0 when it has more data. This is its disadvantage. As you can see here, observations are like this, that sigmoid has values between 0 and 1 only, and the output is non-zero centered also, and the sigmoid saturates and kill gradients because the value it has at the top of the level is out of the gradient terms. And see, at the top and bottom level of sigmoid functions, the curve slowly changes. If you calculate slope, it is 0. You have to see that it can start from here, it is 0, it can end from here, it is 0. So basically it is 0 from both of the ends. Due to this reason, when the x value is small or too big, its slope is always 0. So that's why we can't use in this function in the more bigger data sets. So when we use sigmoid can only be used when you want to get the values between 0 and 1 and at the output layer only. That's it. We can not use this function in the hidden layers or in the other layers also. And when you're doing binary classification, you have the two features also, that is true or false, female or male only, that of features, only then you can use the sigmoid function, otherwise not. So I hope you guys understand the sigmoid function here. Our next thing is tanh or hyperbolic tangent function. The tanh is just another example of function that can be used as a non-linear activity function in our neural networks. It is different from the sigmoid in terms like that the sigmoid can generate values between 0 and 1, but the tanh will generate values between minus 1 and 1. So it can just, this is the simplest difference between the tanh and sigmoid. Like sigmoid function, one of the interesting properties of the tanh function is that the derivative can be expressed in terms of a function itself. We have, this is the function of the tanh and this is the derivative of tanh. You see that the derivative of tanh is also a function in itself. So this is the way we can calculate the tanh here, and it also its derivative, and then we can return those, and we can just make a graph of those by calculating the tanh on the values. And this is our tanh. This is the tanh graph, this is its derivative graph. As you can see that the derivative graph is more likely to be in the sigmoid, but the tanh official graph is like this. It can start from -1 and go to the +1. So I hope you guys understand this graph also, and from the observation we can see that its output is 0 centered. As you can see here, its output is 0 centered, and it is ranged between the -1 and 1. Hence the optimization is easier in this method. Hence in practice it's always preferred over sigmoid function. If you don't want to use a sigmoid, you can use the tanh, but it still suffer the vanishing gradient problem. I can explain the vanishing gradient problem at last, and also I can make a video on that also, problem on that also. So when we'll use it, So usually used in hidden layers of neural network, as its values lie between -1 to 1. Hence the mean of the hidden layers comes out to be 0 or very close to it. Hence helps in centering the data by bringing mean to close 0. This makes learning the next layer much easier, because mostly the outputs of the outputs of the hidden layers are close to 0 or maximally close to 0. So with the help of this function you can make them by bringing mean the close to 0. So the next function is the ReLU function. The ReLU is known as rectified linear unit function. So this is the short is a piecewise linear activation function that will output the input directly if it's positive, otherwise it will be 0. Like it can be 1 or it can be 0. Simple. The rectified linear activation function overcomes the vanishing gradient descent problem, allowing models to faster learn and perform better. The rectified linear activation function is the default activation when developing multi-layer perceptron and convolutional neural network. As you can see here, if it gives a value output as x, if x is a positive, otherwise 0. Simple. Like here, if it is positive value, it will give that number. It will not, it will give 0. That's it. There is no other thing involved in this ReLU functions. That's why this function is the most valuable function in the machine learning or deep learning domain. Says is this the range and nature. It is non-linear, which means we can easily backpropagate the errors and multiple layers of neurons being activated by ReLU function. So this function can be used in the multiple layers of the neural network and uses. The ReLU function is less computationally expensive than tanh and sigmoid because it involves simpler mathematical operations. Like you just have to make a max function work here. At a time, only a few neurons can activate it, making the network sparse, making it function and efficiently and make easy for the computations. The limitations is that it can be only used within the hidden layers of neural network. Another problem with ReLU is that some gradients can be fragile during training and then die. So it can cause weight update and which make it never activate on a data point again. Simply the ReLU could result in dead neurons. Like you have a neuron that you do not need now. So once it can be deactivated, it cannot be activated again. But this function can also be cured with the help of leaky ReLU function. Leaky ReLU function is used to fix the problem of dying neurons modifications by using the neurons. So it introduces a small slope to keep the updates alive. Like you see that our slope is just like the 0, but it can just make it to a very small slope that can update the weights alive. We can have another variant made from ReLU, both ReLU and leaky ReLU functions called max out function. So here the max out function works. Like the leak helps to increase the range of ReLU function. Usually the value of a is 0.01 or so. Where a is not 0.01, then it is called randomized ReLU. Then the range of leaky is -infinity to +infinity. And as you see that before its range is 0 to infinity, but now its range is -infinity to +infinity. Both leaky and randomized ReLU functions are monotonic in nature and the derivatives are also monotonic in nature. So that means both functions are worked very well perfectly in the neural networks, and we can have the two versions of the ReLU function. The first is randomized, where the value of a is not 0.01, and the other is the leaky one, where the value is equal to 0.01. So hope you guys understand about this all the functions, and our next video is basically about the simplest problem, that is vanishing gradient problem. Bonus video for neural networks. In this video I will explain about the vanishing gradient descent problem. So what is the problem and how it can be solved and why it occurs, all the things are explained in this video. So please be with it and watch the full video so that you can understand the most of it. Let's start the video. So the problem is, as more layers under a certain activation functions are added to the neural networks, the gradients of the loss function approaches to zero, making the neural network hard to train. Like if you are using a certain activation functions, like this problem occurs with the sigmoid and 10H. If you use one of them, then with adding more layers into the neural network will make it hard to train, and thus resulting the gradient approaches to zero. So why it occurs? So as you see that the sigmoid function squishes a large input space into a small input space between 0 and 1, because this is the function's true functionality, because this function just get your input and gives you output that is between 0 and 1. So if you give input in the large numbers like 1000, 2000 or 1 lakh, it can just squishes those number into between the 0 and 1. So therefore a large change in the input in sigmoid happens that will change the output. So this I like to show the graph of the sigmoid function, as you see that here. So it is also not a zero centered, and the example is that the gradient of the sigmoid is much smaller than the sigmoid original function. So as example, that this image shows that when how the input of the sigmoid function becomes larger or smaller, the derivative becomes close to zero. So as you see that when the inputs of the sigmoid function become larger or smaller, the derivative close to zero, because the derivative is also way much less than the original sigmoid function. It is very much close to zero. So that's why this happens mostly. So why it is significant? Because why it matters? Because why it matters in our neural networks problems. So this happens when if you have the layers are very much less, like if you have a 2 or 3 layers only in your network, this is not a very much big problem. But if you have a very big neural network which contains around 6 to 8 or 9, 10 hidden layers are there, so then there is a problem, because gradients of neural network are found using the back propagations, and gradients are the just the parameters, or just are the things that we can get in our neural network by using the back propagation. Simply put, the back propagation will find out the derivative of a network by moving layer by layer from the final layer to the initial layer. This is called the back propagation. So by the chain rule, the derivatives of each layer will multiplied down the network and can layer by layer and can get the derivative of the initial layer. Because if you see that if you have the 4 to 5 layers of neural network, like I can show you guys here, like if you have these much layers, this is one layer, this is the second layer, this is the third layer, this is the fourth layer, final layer. So derivative calculated for this layer and add up to this, add up to this, and add up to the initial one. So in this way it can add it up. So when the n hidden layers using the activation function like sigmoid and n small derivatives are multiplied together, thus the gradient descent exponentially decreases to a very much small value. Because like if for the final layer, if the gradient is 0.9, so when it reaches down to the initial layer, it just becomes 0.0.0.1. It becomes so less from the here, because at each layer the derivative becomes small. As you see that the derivative become small at each layer and becomes more close to zero. So that's why the exponential decrease in the gradient. So the small gradient means the weights and biases are of the initial layer will not update effectively. Like if there is a change only of a 0.0001 change in the weights and biases, so they are negligible change in the weights and biases. So that means there is a no change and the iterations occurs. So there is no training happens. So that's why this problem will be significant, and we have to make a solution for that. So the solutions are, we have to use the ReLU activation function as I explained in my last video, and you can use the residual networks also. These networks are just like the a connection between the layers, that it cannot go through the activation functions. As you see that here, it cannot go to the activation function, it can go directly from the one layer to other layer and can add up the values between the blocks. So our other solution is batch normalization. Batch normalization means because the problem arises when the large input space is mapped to a small one, causes the derivatives to disappear. In upper coding, as see that this coding, this thing, so the more clearly seen that when the inputs are big, the batch normalization reduces this problem by simply normalization the input that doesn't reach the outer edge of sigmoid. So we can make sure that the inputs will fall only between this green region where the derivative is not too small. Because as you see that if the inputs go beyond or go forward to these green region, the derivative is too small and it's too negligible that our neural network will face the vanishing problem. So I hope you guys understand this, and if you have any problems regarding this vanishing gradient descent problem, you can just comment down and I will happily to answer your questions. Hello guys, welcome to Freebird's Crew. So in this video I will tell you about the loss functions and the loss functions, that how it works, how can be implemented in Python, and what are its types, and all the things about loss functions. So be with it, let's start our video. So the loss functions are of many kinds, but the nature of a problem should dictate that what should we use. In this tutorial I will tell you about all about the loss functions. So we see that there is a function of called sum of square errors, that it can just first calculate the difference between the actual value and the predicted value and then make a square of it. So this is the sum of squares method. So this is the simplest method I'm going to use in here, but if you want to just get the total, the code of all the functions, you can get into this my repository here, and you can get all the loss functions here. So loss functions are of two types. The first is regression losses, second is classification losses. The regression losses when we try to predict output from some set of finite categories. Like if we have the three categories, mainly star, moon and sun, and we have to just categorize the elements into those three categories, and those type of losses are the classification losses. But in regression losses we have to deal with the continuous numbers, like the age group or the heights or the total number of rooms or anything that is discrete or continuous. So as you see that n is our number of training examples, I is our ith training example, and yi or y true is our the ground truth level of the training example, and yst is the predicted output. So our first regression loss is mean square error or L2 loss. So mean square error of an estimator measures the average square of errors. Like it can first calculate the differences between your actual and predicted output, and then it square those and then get the mean of it. As you can see, MSE is a regress function corresponding to the expected value of the squared error loss. As you can see that I have the HAT, that is the weighted value, this is the true values. So simply make a function, first I get the differences and then squared it and then get the mean of it and then get the square root of it. So by getting the square root of it, I can get a very small value or very decent value that I have to change in our neural network to update our biases or weights. So here, like this is our y hat and y true, you can get our RMS error here. So in this way you can calculate the loss by using the mean squared error function. So our next function is mean absolute error or the L1 loss. Mean absolute error is just between the paired observation. Like if we have two like x and y, So we can compare those x and y comparisons on the basis of their results, on the basis of their times, on the basis of their techniques that we use to calculate both the outputs or anything like that. So MA is more complex because it needs more tools to calculate, but the MA is also a robust, and it can also calculate your outliers and can get it done in a very less time than the MSE, and it does not require to use of square, so it is robust for that. So as you see that we have this our values here, and it can get the differences, get the absolute from here, absolute differences from here, and then it can get the mean. So after it getting the mean from it can just give it the output. This is our output. So this is the simplest form of explaining the mean absolute error, but if you go in the depth of it, you need the linear programmings and the other things to do with it. So these are all the complex terms, but if you want to just learn about what is mean absolute error, so it is basically the term that we use to compare the two same phenomena's observations here. Like I can write here that absolute mean error is a measure of errors between the paired observations expressing the same phenomena, like y versus x, that includes the predicted versus observed, and initial time versus sequential time, one technique versus alternative technique, like comparing the two things. So our other thing is mean bias error. This error is not very much useful in our machine learning terms, but can be useful when the model is biased only in of two terms, like it is positive, it is negative. Like it is not used where the bias or where the loss is a very complex thing here. Like as you can see that this is same as MSE, with the only difference that we don't take absolute values. Clearly there is no need to be caution, as positive and negative errors could cancel each other out because there is no square, and there is no square around here, because that's why it is used only when we know that there is a positive bias, there is a negative bias. Only in those conditions we use this mean bias error. So our next thing is classification losses. So in classification loss, our first loss is hinge loss or multi-class SVM loss. That loss is particularly used in the support vector machines algorithms. So as we know that when we are comparing two categories of image, that the score of a correct category should be greater than the sum of scores of all incorrect categories by some margin. We usually take one. That if these two categories are wrong, then the sum of scores of these two categories must be less than the correct category. So in this way we can calculate these things. So the hinge loss is used for maximum margin classifications mostly in the support vector machines. Although not differentiable, it is a convex function which makes it easy to work with usual convex optimizers used in the machine learning domain. So consider an example here. We have example that to predict that this image is of what, so it can give us these outputs. For dog it can give us these outputs, and for cat these, and for horse these. So by using this formula, by maximizing and by getting the output from here, and by adding +1, because the +1 is for the correct category, so I can get that from here. Like for the first is dog, I can get these three outputs, like 0, as you can say here. This we can just use simply this formula, so you can just concentrate on the formula also. So 0, and then 1.49, and minus this other category minus 0.39 +1. This is our first condition is here, and second we can take these two. So these two is also here, and calculating the maximum function from here we can get these two. So after getting these two we can get plus this and this. So this is the y very high loss, means this is the wrong output generated by our function. So our next thing is for going with this, like in the formula of like this. So maximum 0, we first take these two and then take these two, and after getting the output as 0. So it is correctly a very correct prediction that it is a cat. So our third thing is horse. For horse we can take these two and other these two, and output is 5.2, which is also very high loss. So it is also a wrong prediction. So in this way we can calculate our hinge loss or multi-class SVM loss. So our other loss in this category is cross entropy loss or negative log likelihood loss. So this loss is common setting for classification problems because loss increases as the predicted probability diverges from the actual labor. That when our prediction is diverges from the actual prediction, only then this loss occur. So as you see the formula here, that this is our actual value log predicted value plus 1 minus actual value log 1 minus predicted value. This is the whole formula, and we can simply use this formula in our function here. So it can just use like this function here, that when the actual label is 1 and the second half of function got disappeared because we don't need this function to be here. But when the actual label is 0, then the first half is dropped and we can need this function to be here. So in this function we just multiplying the log of actual predicted probability for the ground truth class. So as you see in the function that we can use the np.cliff function. The cliff function is used to just like we have an interval for 0 to 1. So the values that are less than 0 should be marked as 0, and the value should be greater than 1 should be marked as 1. So it can just clip out or just make those values to be into the interval, so that the cliff function does. So the cliff function here we can use, and it can just use this simple formula to get our cross entropy loss here, and it can get the losses here. So these are all the loss functions here you can learn in this video. And if you have any query, anything like that, you can just ping me, or you can just ping down your query in the comment section. And if you guys like this video, please like, subscribe and share our videos so much that we can reach our maximum subscribers here.